So basically, after introducing your gamma energy, we have now talked about the nuclear reaction rate. So basically, the expression is given by rate is proportional to 1 by E, and also the rate is proportional to your quantum mechanical tunneling probability. ठीक है sir? So if you make this, so sigma is proportional to this E divided by E, and we can write it like this. So this AC is the constant of proportionality, and it has got quite a weak energy dependence, and it is known as astrophysical S factor. Now if I use this, then you will remember that we have done this calculation in our composition equation class, where I have written this expression. That means reaction rate between two species I and X. I have written it like this, using the sigma V. Remember, we have the averaging over sigma into V. Now V means I am talking about, suppose I am talking about two species. So in the sun, can you say what velocity is of one species, what is the velocity of another species? You cannot say. What you can say is that both of them, they follow Maxwell-Boltzmann distribution, right? Relative velocity and all that. So I am just putting in that in the sigma V averaging. This averaging is done by integral over here, and so that V part we will be putting the Maxwell-Boltzmann distribution, and you see this familiar term from the Maxwell-Boltzmann distribution. ठीक है sir? E to the power minus E by kBT. This is the term we talked about in the high energy tail. Okay? Acha. Next this one. So this is the quantum mechanical tunneling part. So two parts are important, and this is just a constant, so it can go up. So basically this reaction rate will be an integration over this function Fe, which you can write like this. Now it is very trivial problem, and you can do this and check that this Fe will have a maximum at gamma peak given by this value E0, gamma peak E0, which depends on temperature and this gamma energy Eg. This is the value. I will ask you, I would like you to do this calculation at home, this one. And next, what about the width of this gamma peak? So basically, what I am saying is that you see, in this reaction rate term, if I put outside this AC, so we have got these two terms, fine. Now look into the energy dependence. One is e to the power minus E, another is e to the power minus denominator. So this means that the nature of the two energy dependencies is quite opposite to each other. And this I have shown over here. You see, this is your Maxwell-Boltzmann tail, this term, and this is your quantum mechanical tunneling probability. You see, the two natures are very different. One is like this, another is like that. And as a result, we will have a maximum peak. And this you can get by differentiating this term. Okay? And after that, if you do a Taylor series expansion, then from there you will get the value of this width. So what does this tell me? This tells me that the entire reaction rate, basically, it is dominant in this part, which is known as the gamma window. And the two very important features of this gamma window is gamma peak and gamma width. And here I have given you the values of gamma peak and gamma width. Now we note that this gamma peak and gamma width, they depend Eg on Eg and temperature. So this is very important. Fine. Now after this reaction rate estimation, you can see I have just given this form over here. You can see that the total energy generation rate depends on Eg and temperature like this. So this is the form. Okay. So next, let us apply these concepts. Oh, one more thing. Now you remember this reaction, proton plus proton forming deuterium plus, right? Now this reaction, now you see, it can be shown that if we use this reaction, if you put in all the values over here, then we can explain the solar luminosity. Okay, it can be shown over there. Now let me compare two particular reactions. One is the second reaction from the PP1 chain reaction, this one, and another is from the CNO cycle, which I will talk about next class. But let me just tell you that this is one of the important beginning reactions of the CNO cycle. Now, hydrogen burning happens through 3 PP chain reactions and another CNO cycle. Now, there is one important difference. In PP chain reactions, what happens is that first proton plus proton, they form 4 helium in the PP1 chain. But in that part, there is 3 helium also produced. And after the formation of this 3 helium, then it serves as a byproduct for another 2 chains, PP2 and PP3. Whereas what happens in the CNO cycle is that trace amounts of carbon, nitrogen and oxygen, they serve as catalysts for hydrogen burning. Now, how can you have carbon, nitrogen and oxygen in a star? There are 2 possibilities. Number one is that at the beginning the star didn't have any such heavier nuclei, so only hydrogen and trace amount of helium was there. So slowly and slowly hydrogen burning is going on. But near the star there is some catastrophic event, some supernova or something like that, from where large number of heavier elements have been deposited inside the star and there are trace amounts of it. Okay, this is one possibility. Another is there is already some trace amount present in the beginning as a result of its formation. Okay, so there are 2 types of possibility, but let me not talk about it. So let me compare, if it is possible to compare these 2 reactions and say something. So first note the nature of the 2 reactions. One is P plus D forming 3 helium plus gamma. Another is P plus 12 carbon forming 13 nitrogen plus gamma. You see the nature is very same, and as a result they are comparable astrophysical S factors. You see the gamma over part and both have proton addition. Okay, now if you calculate the Eg, putting in the various values, you see this value, you get this one. Eg 0.66 MeV for this reaction and it is 32.9 MeV. From this you can do 2 estimates. Number one is, say at your stellar temperature of 10 to the power 7 Kelvin, that means 1 Kelvin, you can do a comparison of the reaction rate of the 2 reactions. And you can see immediately that this reaction is very much slower than this reaction. How much slower? 10 to the power minus 20. I have just used this part over here for doing the calculation. And so this tells me that reactions between species having low atomic number have low values of Eg and they are preferred. This is one information we get from here. Another information that we are getting is that this, you see, what is the temperature dependence? The temperature dependence is like this, coming through this term, 2 terms, right? Now, if you do the calculation, then you will see that in this case, the energy generation rate is proportional to T to the power 4 for this PP cycle, PP1 chain. Whereas it is of the order of T to the power 19 or some 18 to 19. So this means it is highly temperature dependent. So this is the second inference that we get, which is for higher value of gamma energy, the reaction rate depends more strongly on the temperature. Okay, so we have got 2 different observations. Now what I want to do is I want to compare the PP chain reaction with the CNO cycle, and I want to see whether, I want to just check which reaction is the dominant mode for energy production. This is what I want to do. Now for that, I have to remember that the very first reaction in the PP chain, this reaction, this is basically, you see, the time scale. Remember, this happens by weak interaction. So the time scale for this reaction is 18 orders of magnitude greater than this time scale, which is following by electromagnetic interaction. Now if we take this into account and also the temperature dependence of these 2 reactions, along with the fact that this reaction is hindered by this, we come to the fact that basically this reaction, this one, here is basically a bottleneck for the PP chain reaction. If you have a very big bottle, large number of water inside but very small mouth, if we pour in the water out of it, the entire water will not come out. It will be limited by the rate which depends on the small neck of the bottle. So this means that this reaction is basically inhibitor or working as the bottleneck for the PP1 chain reaction. Whereas for the CNO cycle, if I write down the different other reactions as well, you can see that there is no such bottleneck over there. And the end result is that number one, this is a bottleneck reaction. This is inhibited by this is taking larger time, 18 orders of magnitude. Number one observation. Number two, this reaction, this one is slower than this reaction by 20 orders of magnitude. Second observation. Number three observation. Temperature dependence T to the power 4, temperature dependence T to the power 9. So if I take into account these three observations together, what I get is the fact that for mass greater than 1.2 solar masses, CNO cycle is basically the major contributor to energy in stars. Okay, so this is the inference which we can get from this comparison. Any questions? Yes. In the sun, PP1 chain is dominating. Solar